Hey YouTube, today we will be going over these things in order. I'm not sure if I'll be able to finish all these on time, especially the fourth and fifth one. So um, we'll see how far we go. I'll be tackling them one by one in this order. So last time, if you've seen the last video, you would have seen that recursion is a little buggy because a a perfectly fine recursive function is not working right now. So we will have to look at why that is happening. So first, we will um, debug recursion. We'll make a new foo.rkt, which is a Lisp file. It's bigger. So last time we defined a function that sums up uh, all integers in a certain range. So that was some range. Was it range sum? I'm not sure. Actually, you know what? I'll try another extension because as you've seen there, the NeoVim editor keeps complaining about something and I don't know why. So I'll just try to use another file extension and see if that works. Um, so we have a starting number and an ending number and an accumulator. Now okay, oh whatever. So the last argument is actually an accumulator. So it is not, its usage would be not trivial to the end user. But for the purposes of this demonstration, we will be putting the accumulator in the arguments because it is easier for us to test it. So the accumulator is going to carry the sum of all the numbers that appeared from the original starting point to the current position. So if end is larger, smaller than start, then we've reached the end of our range. So we return our accumulator, and then if the range is still valid, we call the recursive function with the parenthesized expression, adding 1 to start, keeping the end the same, and adding start to accumulator. Make sure we have our parentheses right. So this is the last thing we tried while we were trying to test recursion, and it kept taking too long. And my hope was that what I've hoped was that it was taking too long because the recursion is getting too deep. But I don't think that's the case because it takes too long. So maybe I'm thinking it's got some infinite recursion issue. That's what I'm thinking, but we'll have to see. So the problematic part was supposedly this part. Now what we're going to use in while we are debugging this bug is the trace function. So Haskell is known to be a purely functional language, and that also means that they're really sensitive about side effects. So functions that are pure are also functions that do not have side effects, and there's a very useful side effect that is that becomes really handy when you're debugging code, and that is interacting with standard input and output, because we usually print the suspicious things out to standard out, but in a purely functional language like Haskell, where you only get the value, you cannot do side effects such as printing out to the console, because that is, after all, changing something. It is writing to a file. Um, but from what I've heard, there is an escape hatch to it, and that is what trace is. Let's go trace. So the trace function is in debug.trace. So this function accepts a string that is a description of what you're tracing. So for example, you can put variable names inside the string, or integers, as long as you convert them to strings. Anything you want to inspect, and it accepts an arbitrary type, which is the thing that you were using, right, originally in the original code, so that it returns the thing that you were originally using. And it has many utility functions. So the function that we're going to use is traceM, because I think the best thing for us to do is inspect the environment. We have to first see if the environment is being initialized properly. So here I'll be, but notice how we're in a do block right now. So it's not trivial for us to use the trace function, because it returns something. So inside the do block, we use traceM, just like the example does here. So traceM, we want to look at the original environment. We import debug traceM from debug trace, and we also print out the new environment. Okay. Um, mm, mm, mm. Food on RKT does not exist. You are right. Okay. So as expected, and I think it is true, I think the function is recursing infinitely. And the reason why is because, I don't know. But what we can see here is that the states do not change. And apparently they call the same function with the same arguments. And this is problematic because if you wrote this function properly, we know that the arguments values are supposed to change. Except for this one. So how are the new values supposed to be? What are the new values supposed to be? Those are these values here. So this is the original environment, and we're combining a new map that has all of our new values. So we'll see if this map properly contains the things that we want it to contain, which is the new arguments. What should this be? Zip. Okay. What? Okay. So start it has actually changed. So we do know that we have a proper map that contains our new values. This one hasn't changed because our starting value was 0. And if you add 0 to 0, it's still 0. So it would have changed, but it just looked the same. Okay. So I think the new environment is not updating properly. And that's probably this guy's fault. And what I think is happening is this guy override these guys' values because it came first. Probably implicit, but I should probably look at the docs because I didn't look at the docs properly. Haskell data map. Takes a left bias union of T1 and T2. Prefers T1 when duplicate keys are encountered. Okay. So what we should do is switch up these arguments. And I think that'll work. So if it worked properly, it should print out 55, which it does. So now we have a properly working recursion. And we didn't even implement it separately. It just happened to us, which is really nice. So now we'll have clear native functions. So the way native functions are working right now, they make it harder for some code like this to happen. If true, we have plus. Otherwise, we have multiplication times. And you can see here that it should evaluate to a certain function. Since the condition is true, it should evaluate to a plus, which is a native function. And because this is a function, and because this is appearing as the first argument of a parenthesized expression, it should have to correctly compute this thing. And we'll see if it does it correctly. And it gives in an error. We'll see why that is happening. So you can see that the outermost part is a parenthesized expression, which has its first element as also a parenthesized expression. So eval this one. When an expression comes to us, we blindly pass it to apply function, which is fair. Um, so what would happen if our code gets passed to this function? The first thing that is there is a parenthesized expression, which isn't there. We're only handling identifiers, so that's the first reason. And the second reason is, the second problem is, let me just spin up a REPL, and if I type in plus, it should print out that it is a function, but it's not. But it's complaining that it doesn't exist. But I wanted to know that it is a function, and it'll be weird for the user to know that there is a function called plus, but does not let you reference it like this. So let's change the description so that we know if it's a function or if it's native or not. So that's the second problem. And I think the second problem is more straightforward, and it's that it should really be treated as an identifier. It's only being treated as a plus function only when it is the first argument of a parenthesized expression. So it works correctly when it is in parentheses, but it doesn't work correctly outside of parentheses. That's the problem. And we should treat them as real identifiers. It's what we should do. So there is only one part, one implementation that handles evaluating identifiers, and that is we look up the environment, and if it is there, we return it. If it's not there, we complain about it. That's it. And in the environment, is our function inside the environment? The answer is no. So we have a few options. The first option is to implement the native function as like this, which is truly native. And the second option is to if you guys remember, you can see that we start with an empty environment. But we can start by populating native functions to the environment beforehand. So that's an option as well. But let me just think about it right now. I think the option, I think the environment, extending the environment part is more, I don't know, more extensible, more natural. Okay, I'll go with the second way. Then we have to make a default environment variable, and the code will get a little long because it's creating a large environment that has all the native functions in it. So we make a global environment. Map from list. Plus is a plus native function. Native plus function. Native plus. And we'll define natives right here. Oh. We'll define natives right here. And another problem while we are trying to implement native functions is that it only accepts values. Is that a problem? I think it is, because is it? Is it not? Hmm. Hmm. Well, I think rather than accepting values, accepting expressions makes it more extensible, because things like define and let they need to actually look at the syntax tree and look at identifiers. So I think it's better for functions like these to know what the name of the identifier is. Evaluating identifiers does not really make a lot of sense for functions like these. So for these guys, I will pass them as expressions instead of values. So essentially it's just delaying evaluation to use the information in the syntax tree. Now we go back to plus, which is an S expression to value. Yeah. So we changed this to S expressions, which means that these native functions, like each native function, is now responsible for evaluating all of these as expressions. And to evaluate as expressions, I think about evaluating an identifier. You would have to look up the environment. And in this type of signature, we don't have the environment. We need access to the environment, and that is why the type needs to be exec state, like many other functions in this file. Arguments. We map m eval as expression. That will make it a state t with the list of values in it. With the list of values, we need to crunch them and yield the sum of them. So we use fmap. So it's the usual thing. Now that we have the same list of values by applying mapm, why is it complaining? perfectly fine. Oh, okay. Oh, okay. So this is just a Haskell function, but what this guy needs, what this environment needs, is a value type. So we need to wrap it inside native function. We could make this a native function, but I'll just stick with this method right now. Native. We'll go with native. Native sum. Product. Easy as that. So we're porting all these operators. Okay. We'll just move these native functions into a separate file. Can we import types from this file and then export it to the same file? Do I really want to put them in separate files? It kind of gives me a headache. Is it conventional to put types in a separate file? Because what we need are these types. Oh, darn it. Haskell file for types. Separate file for types. Why is it common to put classes and type definitions inside special types module instead of placing them within corresponding namespaces? It's almost always done to avoid circular dependencies between modules. This is the exact problem I'm running into. JC handles them very poorly. They're theoretically allowed, but the mechanism is so painful, they're nearly always avoided. Okay, so in order to avoid pain, I will put them in separate type files. Eval types. We'll just stick them for now. This almost causes pain. Module eval types. Where? How can I export all of them? Haskell export all. Okay, by default, all names are exported. Import S expression. Wait, I forgot the import syntax. Import parser S expression. Okay, this will take a little bit of time. Here's a map. Here's a state T. You have the right map right here. Why are you complaining? Dude. Eval types. now import eval types, value, and XX state. From native, we import from eval types, value, env, and XX states. So the purpose of this file is to only include functions like these, which are native to, which are in the global environment by default. Okay. Let's try stack build. What's the matter? What's the matter, dude? Help me. Oh, right. Import data map. And only import map from. Okay, now it's happy. Native. Import parser. Vietnam. Oh. We'll first copy these utility functions over because I don't think any other functions use them except for native functions. So if that's the case, we will remove it from this file after refactor. So the type constructors are not just imported. Oh no. Oh no. No, 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 no. 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 Oh no. 어떡하지? 큰일 났다. Oh wow. Oh no. Okay, so technically this is a circular dependency. I think it isn't as bad as the first case. Let's see if if this file is able to import from the native file. Cyclic module dependency. Oh no. What are we gonna do? No. No. Hmm. We can't do it. I'll be so sad if that's um think. Oh well, I'll forget it. Get it. It's too much of a headache right now. So we have the native sum and product down. Now we try to for the simple ones first. Native and logical and. Logical or any not forget arg. This one it's a little so the not operator only takes one argument, which is a problem. Okay. Arg. If an empty list comes in, we'll respond with an error. Logical operator only permits a single argument. Or an instance. Requires a single argument. Head. Pattern matches redundant. Couldn't match type. Okay. That was smooth. Native, logical, native equals. What equals does is, I think it's better to do a, arg1, arg2. Two arguments. Exclamation mark. Pretend that I'm mad. Eval S expression arg1. This is a v1. Copy this line. Oh, nice idea. Didn't know I could use this syntax. Native lesser than. Native equals, no, not native equals. It is, oh wait. Okay. Lesser than, function requires 2 arguments. Then we implement if. If function requires 3 arguments. So we ported over all of these, remove them. Now our kind of different things. Oh man, look at all these native functions. They're taking up so much space. I don't know. What's the right way to indent this thing? Native product. What if there are like tons of elements? Doesn't format these? What about this? Okay. Remove trace. Okay, nice. What about 저녁 환경에 native function 말고 들어갈 게 있을까요? 다른 것도 들어가면 이렇게 그냥 verbos하게 냅두는 게 나을 것 같은데 아니면은 그냥 fmap을 한번 써도 될 것 같기도 하고 일단 그냥 냅두겠습니다. 어차피 지금 생김새가 되게 다 비슷해서 이게 좀 중복이 되는 게 그렇게 못생겨 보이지 않는 것 같아요. At least for me. And then logical and or native logical or equals lesser than native if, and that's it. So we also export the global environment because the REPL and the file runner needs them. And instead of starting with an empty map, we use the imported global environment. I place it here. Global environment. I wonder if there's a naming convention for like exported variables, like the one we have, global environments. For a variable. It's kind of cold. For global variable. Lower camel case. Okay. Hoping that I didn't see the wrong one. Let's now see if it works. So in theory, it should work as exactly how it worked in the previous version. We're trying to add features and preserve the ones that we already have. So we'll try to run things like these. Oh no. Okay, I know why. So now, these are stored in the environment, which means that they should be looked up from the environment, and they are treated as identifiers, like variables. So if they encounter a variable, they will look it up from the environment, and they should retrieve these. But are they retrieving these from here? They are. Wait. Oh, okay. From apply function, plus is not a function. Why is this plus not a function? Okay. Native function. This is a native function. So this function takes in a list of S expression, which is this one. So now we know that we should do this. And func. There you go. Now let's do it again. Requires 2 arguments. Great. It's working exactly as before. According to my perfect testing. Yeah. So now, if we type this one in, it should print out native function, and it does. Okay, we succeeded. let's, as a celebration, let us commit right now. Put native functions inside global environment. Now we have clear native functions. More operators, okay. Well, okay, let's go. More operators. We have the negative operator, which should fit perfectly right here. Native subtract. I don't know if it's right the word. It's the right word, but map eval as expression, get num. This is the only part that should be fixed. Fold our accumulator. Oh wait, no. Element, accumulator. Spin up GHT real quick. Fold our we have a list like this. What should it do? I think we should use fold L. And there was this thing about fold L that people were really cared about, like this one, fold L prime. Yeah, there was a thing called fold L prime. Small until the very last moment when it's already too late. Reduced like this. There would always be a regex. The main reason that I want to use fold L is because if it has a single argument, the first argument should be applied a negative sign. So if it's positive, it should be negative. If it's negative, it should be positive after applying that function. If you use fold R, that won't happen. And I want it to be consistent at the very least. Okay, this thing, it is lazy. So it still has problems. This thing, I suppose that it is strict. Except for their strictness property. So if both return a result, it must be the same. It's the more efficient way to arrive at that result because it doesn't build a huge thunk. If the combined function is lazy in its first argument, fold L may happily return a result where fold L prime hits an exception. Oh, okay. Okay. So it tries to evaluate. But I don't think we have that problem, so we'll use fold L. Fold L prime. Fold L prime. What shall we do? C is a function. Fx, zfx. What is zfx? Oh, so this is the accumulator. But why is z right here? Oh, okay, it's being applied here. So z is the first argument is the accumulator. Second is the element. So oh, I don't know. Let's just try it out for ourselves. So this should return -1, -2, -3. Oh. Great. Exactly what we wanted. 0. Okay, perfect. Now we implement the remainder, the modulo operator, and the division. Division, I only want it to have 2 arguments at a time. Divide, modulo. Modulo mod. Let's see how it works. It's 0, 2, 2 as well. 2. Okay, it's working correctly. Great. More operators completed. Can we implement nested define? Oh. Let's commit first. More operators. Um, hmm. I think nested defines are not a good fit for a language because right now, is it? I mean, it's not strictly necessary. And the thing is that we have this very strict rule that parenthesize expressions. Oh, never mind. Hmm, 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 hmm. I don't think it is necessary. I don't. Uh, the reason I wanted to, the reason I thought about doing this was because there's a similar construct in Racket, and I really enjoyed using it because the define function is um, only valid in the scope that it is defined in, and it's a really useful feature. So you can define functions inside functions, um, which is really useful. But I think this feature is out of our scope for this language, whose goal was to implement the essential features. And I don't think it is essential. Um, this one I'll be implementing in another day. I have to go to church tomorrow, and it's 1:30 in the morning. 그래서 오늘은 여기까지 하도록 하겠습니다. 그래도 오늘 꽤 많이 했어요. 여기까지 하겠습니다.